In this video, we will be demonstrating the strain gauge trainer, the SM1009 from the Materials Testing and Properties range from TecQuipment. By allowing students to experiment with 3 different structures to test tension, torsion and bending using resistance strain gauges, students can practically learn real-world methods of measuring strains in different structures. Most engineers use strain gauges. For example, structural engineers use them to find the strain in the supports of buildings and bridges under load. Mechanical and aerospace engineers use them to find the strain in machine parts in different shapes under pressure or load. This bench-mounted system is self-contained and can be operated by gathering data more simplistically using the digital strain display or TecQuipment's versatile data acquisition system, VDAS. It contains everything needed to show students how resistance strain gauges work and is ideal for group work and classroom demonstrations. Let's take a look around the experiment. The main part consists of a sturdy frame that holds 3 common structural systems: the tension system, the torsion system and the bending system. Included are a set of large weights for use with the tension system and small weights for use with the bending and torsion systems. It also includes extra items such as a vernier caliper. By using the theory and the known dimensions that are included in the comprehensive user guide, you can calculate the stresses and strain in theory and then compare them with measurements from the strain gauges that you've gathered yourself. Students learn how to compare the performance of quarter, half and full bridge strain gauge connections for each structure. Now to look more closely at the tension system, which allows you to understand how much load or force a part or a complete structure can take. The tensile test specimen, which comes in steel as standard, shows the strain in terms of the stretch along its axis. The clamp holds the test specimen and then you add weights to this weight hanger at the bottom here. There are 2 sets of T rosette strain gauges that measure the strain in 2 directions on each side of the specimen. If you want to investigate other materials, we do also supply as an optional extra aluminium, copper and brass specimens. Experiment 4 in the user guide shows students how to connect strain gauges to measure strains in 2 dimensions and compare the displayed tensile strains and theory and prove Poisson's ratio. Over to the torsion system for looking at twisting, i.e. torsional shear strain on the surface. The setup we have here is similar to the torsion bar used in suspension cars. It consists of a solid circular section torsion beam, which is a bar held by 2 fixings that can be rotated or twisted independently of each other. You can also clamp one at an end as well. At this one end, a clamp holds the beam in place and a free moving beam holds the other bend. The bearing is also a second support that removes any bending moments in the beam. A moment arm fits into the bearing so that you can add weights to twist the beam. You can see here 2 sets of torsion gauges that measure the torsional shear strain on the surface of the beam at 45 degrees. With experiment 3 in the user guide, students learn how to use shear and torque strain gauges, calculate the force and torque for each load. Then by using these equations, they can work out the polar moments of inertia for the beam, the shear stress of the beam, shear modulus, and then the shear strain, and finally the direct strain. Finally, we have the bending system that measures the tensile strain on the top of the beam and the compressive strain underneath the beam. In the real world, you might think of an aeroplane wing, a swimming pool diving boards, shelf supports, bridges and balcony supports on buildings. There is a solid rectangular section cantilever beam held securely at this end. 4 strain gauges measure the tensile and compressive strains directly in line with the beam. The 2 on top measure the tensile strain and the 2 underneath measure the compressive strain. The first experiment in the user guide takes you through getting to know this part of the equipment, guiding the student through creating a quarter bridge connection, half bridge connection with opposite arms, then adjacent arms and a full bridge connection. You then record and chart the results to answer questions such as, do your findings prove the Wheatstone Bridge theory? The second experiment looks at bending and takes the student through adding loads, taking measurements and calculating the Young's modulus. Separate to the mainframe is the strain display that includes a set of high accuracy dummy strain gauge resistors, these are plugs, and the controls. These allow the student to connect the strain gauges on the structure as quarter, half or full bridge networks. The strain display works with and gives correct readings for all bridge connections and different gauge factors. An extra setting on the strain display works with the tension system to prove Poisson's ratio. The strain display has a socket for connection to TecQuipment's optional versatile data acquisition system, VDAS. A separate VDAS hardware unit is required if you plan to utilize the data acquisition and analysis capabilities of the VDAS system. Lastly, you might have noticed these mimic diagrams on the back plate that show you what each gauge looks like and how it connects and how it fits on each structure. That's it for the strain gauge trainer today. If you're looking to assemble your own strain gauges, TecQuipment provides the strain gauge kit, the E19, with the digital strain display, the SM1009. For more information about all of these, click on the links below. Thanks for watching.